We're going to learn about conformations of alkanes. One of the big things about conformations is strain, and strain is the instability within a structure associated with internal energy. Okay, so now we're going to talk about conformations. Conformations occur in alkanes with two or more carbons in which are any 3D arrangement of atoms in a molecule that result from a rotation around a single bond. A great way to view conformations is by looking at Newman projections, which is a way of viewing a molecule by looking at a carbon-carbon single bond. As you can see here, we have an eye looking at a molecule, butane. You see that's looking on a single carbon-carbon bond. So now we're going to see that there are 6 different types of Newman projections for one molecule of butane. So there's 2 different ways of defining the different Newman projections. So we have eclipsed, as you can see here, and staggered. The eclipsed ones are when the substituents are right on top of each other, and the staggered ones are when the substituents are as far apart as possible. So between the eclipsed ones, there's 0 degrees between the substituents, and between the staggered ones, there's 60 degrees between the substituents. And when I say degrees, I'm talking about a dihedral angle, which is an angle created by 2 intersecting planes, each defined by 3 atoms. So between these, like I said earlier, 0 degrees, and between this, from the eclipse, there's 0 degrees, and from the staggered ones, there's 60 degrees. But we have, because there's more than just hydrogen substituents, we have methyls as substituents in here. We can talk about what different names that we use. We have gauge and anti. So gauge is when the methyls or the substituents are about 60 degrees apart, and anti is when they're 180 degrees apart. So as you can see, this energy diagram follows the order of these Newman projections. And so when you go from eclipsed to staggered, the energy is from high to low. So what happens is these have, eclipsed have the highest energy because they're the least stable, and staggered have the least amount of energy because they're the most stable. Molecules have an optimal structure that they want to be in. When you mess with that structure, you cause strain on it. And so when you release that strain, you go from more stable to least stable. So that means that it goes back to the optimal structure. And so the ways that there are 3 different types of ways that we can cause strain on a molecule of any conformation. We have torsional strain, which is when a non-bonded atom separated by 3 bonds are phased from a staggered projection to an eclipse due to small donor-acceptor interactions between orbitals. You have steric strain, which is non-bonded atoms separated by 4 or more bonds that are forced closer together than their radii will allow. And we have angle strain, which is bond angle, where bond angle is either expanded or compressed compared to its optimal values.
We're going to talk about cycloalkanes, and there's a few things you should know, such as there's a small ring strain that exists in structures with less than 6 carbons because the bond angle between the carbon-carbon is less than 109.5 degrees. And this is cyclopropane. Cyclo meaning that all the carbons are connected together, and propane meaning 3 carbons. There exist 6 pairs of CH bonds with considerable torsional strength, and the angle between the carbon-carbon is 60 degrees. In cyclobutane, there's 8 pairs of CH bonds, and in the planar conformation, the angle between the carbon-carbon is 90 degrees, and puckering decreases torsional strain but increases angle strain that's caused by compression. And puckering is a different type of conformation that's also known as non-planar conformation. Another thing you should know is that bonds can only rotate so far without breaking the ring. This is a cyclopentane structure, and there's 10 pairs of CH bonds, and the bond angle between the carbon-carbon is 108 when it's planar with very little strain. With a little twist between the carbon-carbon bond, it can transform into its envelope conformation, which has a bond angle of 105 degrees, and it has a decrease of torsional strain, but an increase in angle strain. This is a cyclohexane, and the carbon-carbon bond angle is 110.9 degrees with little angle strain. The adjacent carbon bond atoms are staggered, meaning they have minimal torsional strain. This is a cyclohexane in its chair conformation, and I numbered each carbon on the cyclohexane and in the chair conformation so that you know which carbon goes to which part of the chair conformation. And in each chair conformation, there's always an axial group and an equatorial group, And notice that the axial groups always alternate at each carbon. So does the equatorial groups. And every time you have an axial up, you always have a equatorial down on the same carbon, and vice versa. And chair conformations usually have generally have little strain. With a bit of twisting on the carbon-carbon angles, it will turn into a boat conformation, which is generally less stable due to the torsional strain between the carbon and hydrogen bonds and the steric strain between the two flagpole hydrogens, which would be at the axial up positions. With more twisting along the carbon-carbon atom, you will get an alternate chair conformation, which is essentially just the chair conformation flipped. And in this case, your axial groups will go equatorial, but if your axial group was up, it would remain equatorial up. And once again, these also interchange between each carbon-carbon atom. And this is an energy diagram showing that the chair conformation is essentially at a lower energy state, meaning that they're more stable. And when you have larger substituents, they prefer to be in the equatorial state because equatorial is generally more stable than axial. The substituents, the more they prefer to be in an equatorial state due to stability.